Now, we've spent a lot of time talking about normal stress and the geometric change that comes along with that, which we call normal strain. But one thing that we haven't talked about is what is the geometric change with a shearing stress? Because it's not going to be a normal strain. So it's going to be different. Let's look at our complete state of stress. So this is our little cube that's got all of our forces on it. In particular, what I want to look at is, I want to look at this guy right here, or any of these guys, these shearing stresses. Now remember, the notation in this means something. So tau yx is telling me that I have a shear force on a y-plane working in the x direction. You know, if you go back to strength of materials books from 15, 20 years ago, maybe 25 years ago, you wouldn't see this nomenclature for normal stress. You wouldn't see sigma x. What you would see is you would see tau xx. So talking about a force on the x-plane working in the x direction. And relatively recently, like I said, 20, 30 years or so, we've switched over to that sigma to denote that that is the normal stress. If you look at some of the more advanced strength of materials books, you'll still see it listed out as tau xx. But we're not worried about the normal, we're worried about the shear. So tau yx is a force that is on the y-plane, but acting in the x direction. That's not going to give us a normal stress. The reason that I say it's not going to give us a normal stress is, unlike our sigma x, what's happening is it pulls this way, it pulls this way, and so we're getting longer in both of these planes here and here. That's kind of what's going on with our shear, because if we look at it, I have a tau xx. I have the tau yx that's here. But then I also have a tau xy. Now, one thing to keep in mind, we're talking about shear stresses that, ooh, that was pretty. Let's change that to a pen. Tau xy and tau yx, they're the exact same thing. And they have to be by principle of static equilibrium, because one's causing a rotation. Tau yx is causing a rotation in the clockwise direction. Tau xy is causing a rotation in the counterclockwise direction. They have to balance themselves out. So what does that mean? What kind of geometric change are we looking at? So if I look at this guy right here, these kind of stresses are causing an angular change. As you can see, they're trying to turn our cube into a rhombus. So let's look at things and just go straight with the yx plane. Kind of make it a little bit simpler to see. So here's yx. Here's my element. And then I have tau yx, tau xy, and then actually I do have them on the other side on the 2D element to completely nullify anything out. And so what happens? Well, these normal stresses are going to cause a strain, but we're going to be causing what we call a shearing strain, which is an angular deflection. So we're going to be getting a shear angle. We will not be getting just a normal distance. And so basically what it's trying to do is it's trying to turn my little rectangle into something like that. This is the x and y. So what we have is we have a shear angle here and a shear angle here. So basically we would end up calling these half angles. And the way that we denote that is we're going to continue our classical Greek education. And we're going to go with this guy here. Now the way I draw it is a little bit different than the way you'll see it typed in the book, because I can't do it. The book looks a little bit more like that. So, but this is lowercase gamma. And so lowercase gamma is what we're using to represent the shear angle. So as we look at it, and so this guy would be gamma xy divided by 2 because it's a half angle. And so this one over here would be gamma xy divided by 2. And then what you would have in here is going to be that pi over 2, which is 90 degrees, minus the shear angle. Now let's talk about that. Much like we have Hooke's law for normal force, or Hooke's law for normal strain, we have I can't speak this morning. We have we have a similar equation for shearing strain. Same things apply. We have a material that is in the linear elastic region, so we know it's going to pop back. And so Hooke's law for normal strain tells us what? That, we've got the stress in the x direction is related to the strain in the x direction by a constant of proportionality, which we call the modulus of elasticity. So we do have one for shearing stress, shearing strain. So tau xy, that's our shear stress, it gets related to our gamma xy. So this is our shear angle. But we have a new constant of proportionality, and we're going to call that constant of proportionality G. And this is what we call the modulus of rigidity. This is a measure, let me make sure I'm spelling that, rigidity. Modulus of rigidity is a measure of how resistant something is to being twisted. That's really all it comes down to. If you think about it, modulus of elasticity is how resistant the material is to being yanked on and pulled. Modulus of rigidity is how much that you're able to twist something. And so this would be Hooke's law for shearing strain. Now, we have an interesting thing coming up now because we have 3 properties that all deal with dimensional changes. Modulus of rigidity, modulus of elasticity, Poisson's ratio. And there is an important relationship between the 3 of them. So we can say, if we take the modulus of elasticity, divide it by twice the modulus of rigidity, we can say that that's going to equal to 1 plus the Poisson's ratio. This is a very important relationship because a lot of times books will not publish all 3 of these material properties. You can usually find modulus of elasticity and Poisson's ratio very easily. Modulus of rigidity, not so much. But if you know 2 of these, in this case, modulus of elasticity and Poisson's ratio, you can find the 3rd one fairly easily. And just one thing, so if you've got a high modulus of elasticity, modulus of rigidity, that material is hard to deform. Because it does not want to deform. It just doesn't want to do it. If you have a low modulus of elasticity, modulus of rigidity, it's easy to deform. And so we can use this in conjunction with everything else that we have to figure out material properties and figure out what's going to happen. And this is a very important relationship within strength of materials. But once again, this only works in the linear elastic region. I keep harping on that because for everything that we do in this class, it comes down to it has to be linear elastic. Because once we're in the plastic region, the relationships of all these properties with each other change.